Hi, this is Dane Quinn from the University of Akron, and I'd like to welcome you to my series of video lectures on engineering mechanics. Today, I'd like to focus on linearization of mechanical systems. So when we derive the equations of motion, oftentimes those equations end up being nonlinear. But under certain conditions, we can linearize those and find an equivalent sort of spring mass damper model. Here's the example that we'll look at today. We have a bar of mass m and length L that is pinned at one end, say O. Now, there's gravity acting on the system and a force of magnitude F applied horizontally to the end of that bar. Finally, there is a torsional damper acting at the contact point. So I'd like to define the equations of motion and then linearize those equations about the equilibrium position. So just like always, we're going to start off and we're going to think about this problem for a second. Look at the motion, degree of freedom, and identify the forces that act on that object so that we'll set ourselves up to then go and really derive the equations of motion and model this object appropriately. So what does this thing do? Well, the bar rotates about point O. I mean, there's a pin that exists at O that constrains the bar to, again, rotate about that point. So with a single coordinate, we can specify the configuration of this bar. And it's a single degree of freedom system. So again, any coordinate will do, but we're going to look at the rotation of the bar. What forces act on this object? Well, we have the external force, F, that's shown in the figure. We also have the gravitational force, right? So there's a force due to gravity. There is a reaction force acting at O. And then finally, there is a damping moment due to the torsional damper at the pin joint O. You could think about this as maybe modeling some dissipation that's present in the joint between the ground and the end of the bar. So let's go and include those on our force diagram. So we have this force F that is applied to the object. We have the weight of the bar, right? So that's going to be W. We have a reaction force. I don't know anything at all about this, right? I don't know magnitude, direction, anything really. And then finally, we have a moment due to the damper. This is it, right? These are all the forces that act on our object. So as we go forward, right, we need to make sure that we include these in our, for example, free body diagram. Now we turn to coordinates and directions. We'll define directions I and j to be fixed in the ground, horizontal and vertical, as we always do. Right, so let's go and place those, say, here and there. Then we'll define a second set of directions, E1 and E2, that are fixed in the bar. So here, let's assume that E1 is perpendicular to the bar and E2 is along the bar. Finally, we will identify a coordinate, theta, that describes the rotation of the bar, or can be used to relate I and j to E1 and E2. For example, E1 can be written as cosine of theta in the I direction plus sine of theta in the j direction. E2 can be written as minus sine I and cosine of theta in the j direction. I can also write E1 and E2. I can also write I and j in terms of E1 and E2. So I is cosine of theta in the E1 direction, now minus sine of theta in the E2 direction. And J is sine of theta in the E1 direction plus cosine of theta in the E2 direction. Maybe you want to pause the video now, work out these direction transformations. So if I know theta, I know the orientation of the bar. Our next step is kinematics. So we'd like to describe the motion in terms of these coordinates and directions that we just identified. And in particular, the angular acceleration of the bar is alpha, again of the bar, theta double dot in the k direction. Notice that here k comes out of the board and is the third direction for both of these sets of bases. Now, I usually choose my directions as right-handed when written in the plane so that that third direction k always comes out of the board or out of the plane of the paper, and in particular is the same for both ij and then k, e1, e2, and then k. Just makes it much easier to relate directions and coordinates and things to one another if that third direction is always the same. Now that we have coordinates and directions, we've used those to define the kinematics. Let's also use them to define the forces. So going back and looking at how we define these, the external force, well, that's given to us as F in the I direction. Not much I need to do with that. The weight is minus mg in the j direction. The reaction force, again, I don't know anything at all about this. So I'll just break it up into components, Rx in the I direction plus Ry in the j direction. And then finally, the torsional damper produces a moment. And this moment, as you might expect, is proportional to the angular velocity of the bar. So this moment due to the damper is equal to minus bt times the angular velocity of the bar. Right, so bt is the torsional damping coefficient, and now minus omega so that it opposes the direction of the angular velocity. In this case, using this angle theta, we see this can be written as minus bt times theta dot in the k direction. This is equivalent to a torsional spring, which of course would be proportional to the angular displacement of the bar. So here we have these forces, and I'll add this one in, minus bt times theta dot in the k direction. Right, so this is a moment. These three are forces. And we're ready to apply the equations of motion. For this bar, we will apply angular momentum balance about the pin joint at O. I'll remind you from our background in dynamics that taking angular momentum balance for rigid bodies, we typically have three places that we'll take angular momentum balance, and it, for planar objects, reduces simply. One of those would be about the mass center. I can always take angular momentum about the mass center. However, if I do that, I will have, notice, moments from this reaction force that will be introduced to that. If we have a object that's rolling on the ground, we can take angular momentum balance about the contact point. That is not the case here. But our last case is if we have a point that is fixed in the ground. So O, notice, is fixed in the bar and is fixed in the ground. We can take angular momentum balance about that point and apply the sum of the moments about point O is the moment of inertia about point O times the angular acceleration of the body. The advantage of doing that is that, again, the moment produced by this reaction force drops out. I will remind you from our parallel axis theorem, the moment of inertia about O is equal to the moment of inertia about G plus the mass times the distance from O to G, or the magnitude squared. Now, let's just go and apply this, right? Moments, remember, are R cross F. So here, for the weight, it's the position of G with respect to O, right? So that is minus L over 2 in the E2 direction. E2 is defined as this upward and to the left in this configuration direction, right? So the position of G with respect to O is minus L over 2 E2 cross the force, minus mg in the J direction. Then, for the force at the end, we have minus L E2. Again, that's the position of this end point, say A, with respect to O, cross F in the I direction. Then we also have this torsional moment, so that's minus BT theta dot in the K direction, and this equals ml squared over 3 theta double dot in the K direction. Right? ml squared over 3 is the moment of inertia of a bar about the end. Here, this would be ml squared over 12, right? That's the moment of inertia about the center, plus m times L over 4, or sorry, L over 2 squared. So this ends up being a fourth plus a 12th, gives me a third. Okay, so I need to take these cross products. Well, here I will remind you that we need to write E2 in terms of I and J, or J in terms of E2. Let's write J as sine of theta E1 plus cosine of theta E2, right? That was from the previous slide, right? So J is sine plus cosine. I is cosine E1 minus sine E2, right? So we'll make use of that here. I is cosine E1 minus sine of theta E2. And then we'll work these cross products out. E2 cross E1. Well, here, the way I remember cross products, E1, E2, K, right? And then, of course, we can add in another that. If I cross this way, it's positive. If I cross this way, it's negative. So E2 cross, well, let's look at this one. E2 cross E1, right here, is equal to minus K. So this term is minus mgl over 2 sine of theta in the K direction. E2 cross E2 is equal to 0, right? So we don't have to worry about that. Again, E2 cross E1 is minus K. So this becomes plus F times L cosine of theta from here, minus BT, the torsional damping coefficient, theta dot in the K direction, is ml squared over 3 theta double dot in the K direction. And again, notice that we have eliminated this reaction force in both the components. If I needed to know these, maybe I was looking at the force applied to see if this pin joint would, survive this motion, I could go back to linear momentum balance, sum of the forces equals mass times acceleration, and then once I solve for the motion here using this, I can go back and find out these reaction forces. Here I'm just looking for the motion, right? So there's no need to go and apply linear momentum balance. Combining this, sort of rewriting it, the equation of motion becomes ml squared over 3 times theta double dot plus bt times theta dot plus now these two terms, And when I bring these to one side, I get mgl over 2 sine of theta minus f times L cosine of theta is equal to 0. So this is the equation of motion for this system. Notice that it's nonlinear because sine of theta and cosine of theta are nonlinear functions. Remember, a linear function is something that looks like, well, in this case, k times theta. Anything else is nonlinear. However, for small displacements, we can usually find a linear approximation. So for small displacements, we can approximate these functions, both sine and cosine, with linear functions. Because, I mean, really the problem here is I don't know how to solve this. I don't know how to solve this equation with the sines and cosines. If we had something simply here that was like a k times theta, well, this would again look like our spring mass damper system. We'd have equivalent mass, we'd have equivalent damping, we could identify equivalent stiffness, and then we could go and solve. But I don't know what the solution to this equation is, right? And in fact, the solution to this equation is, well, involves things like elliptic functions and stuff that we typically don't learn about as undergraduates. More importantly, these nonlinear equations do not follow superposition. So I can't come up with a solution and then come up with another solution and then, add them together to get the general solution. Nonlinear equations are just much more difficult to work with. So we would like to come up with a linear approximation for this system. So that kind of brings us to the real topic of this lecture, is linearization. So any function can be linearized using a Taylor series. You may have, at this point, you've learned about Taylor series. You may recall that if I have some general function, g of x, I can define a Taylor series about some point, right? So let's take that point as, we'll do that in pink. Take that point as x0, x0. So the Taylor series says that g of x is g evaluated at the point, plus now the derivative, dg dx, evaluated at that point, times x minus x0. And then there's additional terms, right? There's a second derivative evaluated at x0. Now times x minus x0 squared divided by 2. And I could keep going with this. So how can I linearize this? Well, remember I said for small displacements. So if x is close to x0, right? So the response of this system doesn't stray too far from this point, then x minus x0 is small, right? Okay, fine. But that also implies that this quantity, which is x minus x0 squared, is really small. Imagine this was 0.1, just to pick a number. Then this would be 0.01. And the next term, well, that would be 0.001, and so forth. So when I linearize, I basically assume that x is close to the point that I'm linearizing about, and so we neglect all of these higher order terms. And we just keep that linear approximation, because that's what this is. This is just a linear approximation to this function. I can think about this process geometrically using the slope of the function, right? So here I've just shown some general function g of x. Turns out this is a cubic polynomial as I've drawn it. And at any point, I can identify the slope. So let's assume that the base point was maybe x0 at the origin. Then I can approximate this function by a line, right, whose slope matches the function at the origin. And this line is our linear approximation. Now, if I were to choose some other point, right, maybe I chose this point as my origin, then now the slope changes and the linear approximation changes. I can keep going with this, right? I could go and maybe take a point over here, x0, and now my linear approximation, again, has a different slope. So for these nonlinear functions, the linear approximation depends on what point you take as your base point. As an example, again, this is a cubic equation, right? So let g of x be equal to maybe x minus x cubed. So when I expand this in a Taylor series, right, I would get this evaluated at the base point, x minus x cubed, right? So this is some point. Could be any one of these 3 points. Then I take the derivative of this. So I get 1 minus 3 evaluated at x0, so it's 3x naught squared, times x minus x0. And again, these higher order terms that I would really neglect. So here, this piece represents the slope of this function. And this would be my linear approximation. Now, then the question is, well, what point do I choose as x naught? Well, mechanical systems they typically oscillate around equilibrium points. So if you look for the equilibrium points of your system, then our response usually stays close to those, provided the initial conditions are close to the equilibria. Right, so I've kind of drawn that here. Imagine I've got a system and I've got a bunch of different responses, each shown in different colors. Here, this dashed line would represent the equilibrium value. So as t increases, the system doesn't change. Right? That's what it means to be an equilibrium point. And then if I started off close to that, so maybe I give it a little initial velocity in the purple line, right? It just kind of oscillates about that. Some initial position, displacement from that, maybe a little initial velocity, and again, I get a slightly different oscillation. But again, they're always sort of oscillating about this equilibrium point. So think about a general system, right? It might be mx double dot plus bx dot plus, now again, g of x is equal to f. So this could be a nonlinear stiffness kind of function. Well, the equilibria satisfy the equilibrium equation, which is g of x equilibria equals f. Because for an equilibrium point, x dot is equal to 0, x double dot is equal to 0. I mean, that's what it means to be an equilibrium point. So now, this equation of motion that I started off with, well, I can expand g in a Taylor series, right? So I end up with mx double dot plus b x dot plus, now, g of x equilibrium plus dg dx x equilibrium times x minus x equilibrium, right? And then all those terms that I threw away, which equals f. So this term in this equation cancels out with this forcing on the right-hand side because they have to satisfy the equilibrium conditions. So what am I left with? Well, I'm left with a mass term, a damping term, and a stiffness term. So here, if I measure from static equilibrium, as we've talked about before, with a variable z, so z would be x minus x equilibrium, then z dot is equal to x dot, z double dot is the same as x double dot, and this equation of motion can be approximated with a linear equation that looks like mz double dot plus b times z dot plus, let's do that in red, the slope evaluated at the equilibrium point times z equals 0. So here, this becomes the equivalent stiffness of my system. And it's determined by essentially taking the response of the forcing and linearizing about the equilibrium point. Okay, so, that's a lot. I get it. Let's go and kind of see how this works in practice. And we'll go back to the equation that we started off with, that we had from our model. And I'm going to look at a simpler case, namely f is equal to 0. This is actually a simple pendulum equation. So we have our ml squared over 3 theta double dot. We have our torsional damping. And then this is the restoring moment from gravity. If we think about this as g of theta, then here is that function plotted versus theta. Looking for the equilibria, we find that there is an equilibrium point at the origin. Right? Here, this vanishes at the origin. Right? So theta's equilibrium is equal to 0. As a result, I can linearize sine of theta. Right? So sine of theta is equal to sine of theta equilibria plus, now the derivative is cosine, so I get cosine of theta equilibrium times theta minus theta equilibrium, and then we throw away the higher order terms. And so for this equilibrium point, sine of theta, and you probably knew this, is approximately theta. Okay, awesome. Let's just take that and substitute it back in. So my equation of motion is ml squared over 3 theta double dot plus bt times theta dot plus mgl over 2 times theta is equal to 0. And this is valid for small theta. Right? So for small oscillations, again, we've taken this original nonlinear function and we've replaced it by a linear approximation. We can identify the equivalent mass as ml squared over 3. The equivalent damping is just bt here. And the equivalent stiffness is mgl over 2. As a result, I can calculate my response parameters. Natural frequency, square root of k equivalent over m equivalent. So that becomes mgl over 2 divided by ml squared over 3. And we end up with 3 mg over 2L. So this is the natural frequency for this bar pinned at the end for small oscillations. Likewise, the damping ratio is B divided by 2 square root of k equivalent times m equivalent. And a little bit of algebra, square root of 3 bt divided by ml square root 2gl. So this is the natural frequency and damping ratio for this system, again, valid for small oscillations based on this small angle assumption. So this is an example, this pendulum example, we'll see frequently in this class. Now I want to turn to the case where f is non-zero. That's a little more complicated because the equilibrium point is no longer at the origin. Remember here, this is like g of theta. And so this equilibrium point is no longer at the origin. Instead, it's offset at some new value. And that offset, the equilibrium value, depends on m and g and l and f, and it's basically solving this function for 0. Okay, but I can do that. So for the equilibrium points, well, they have to satisfy mgl over 2 sine of theta equilibrium minus f times l cosine of theta equilibrium equals 0. And fortunately, this is not so bad. I just find that tangent of theta is equal to, well, f times l divided by mgl over 2, or 2f divided by mg. So now, given this equilibrium point, I want to linearize this function about that. Okay, great. Sine of theta is sine of theta equilibrium plus cosine of theta equilibrium times, again, the difference. And we can linearize cosine in the same way. Cosine of theta equilibrium. Now the derivative of cosine, remember, is minus sine. Once again, times the theta minus theta equilibrium difference. Okay, so what we're going to do now is identify this difference, just like we are essentially we're measuring from static equilibrium. All right, so let phi be this difference. So phi is the measurement from static equilibrium. As a result, the equation of motion is ml squared over 3. Now phi double dot, this is constant, so phi dot is theta dot, phi double dot is theta double dot, plus bt times phi dot. And now, plus all this other stuff. mgl over 2. And then my approximation for sine is sine of theta equilibrium plus cosine theta equilibrium times phi. And my approximation for cosine is cosine of theta equilibrium minus sine of theta equilibrium times phi. So again, there's a lot of algebra here. I get that. But the procedure, hopefully, is relatively straightforward. We're taking these nonlinear terms, and we're just finding the slope of the resulting function at the equilibrium point, because we expect that this system will really oscillate around this point. So here, we can continue on, and we find ml squared over 3 phi double dot plus bt times phi dot plus, now because we chose this as an equilibrium point, this term cancels out with that term, and we are left with mgl over 2 cosine, and I'll factor out the phi, and then here and here plus F times L sine of theta equilibrium times phi is equal to 0. So once again, kind of thinking about this geometrically, I have identified this as the equilibrium point, right? So this is theta equilibrium. I've calculated the slope and the linear approximation, and then I'm measuring the difference from that as phi. So if I had a point here, right, I can calculate the value of theta, or the value of phi is theta minus theta equilibrium. So when I do this, and now at this point I've done a bit of algebra, just because I think it looks, it ends up being interesting, that the final result, you can actually go and figure out what cosine and sine are, evaluated at theta equilibrium. And ultimately, the solution is, or the equation of motion is ml squared over 3 phi double dot bt times phi dot. And this stiffness ends up looking like, let's do this in red, L times square root of mg over 2 squared plus f squared times phi is equal to 0. So this is the equivalent stiffness. The equivalent mass here is ml squared over 3. The equivalent damping is just bt, and the equivalent stiffness is L times mg over 2 squared plus f squared. Notice that if f was equal to 0, then this just becomes mgl over 2, which is what we found in the previous case. mgl over 2 if f was equal to 0. But now, the addition of this force at the end of the bar, it actually changes the effective stiffness of the system. And it does so through this shift in the equilibrium points. So when we linearize equations, we can now account for changes in the equilibrium points, right, through the Taylor series of our nonlinear functions. Admittedly, what we're doing on this slide is fairly advanced. Mostly we'll focus on things like this, right, where maybe we just have a pendulum that's hanging straight down in the equilibrium point, so that the linearization is relatively straightforward. We can just use this small angle approximation. But I do want you to be aware that changing the static equilibrium position of a system, right, can have a significant influence on things like the effective stiffness of the system. This is important for problems like vehicle design. So if you're a suspension designer, right, for an automotive company, you really have to take care to know the mass of the vehicle when tuning your system for a specific frequency and a specific stiffness of the suspension system. Right? So these really are important problems. And it's important to know about this kind of thing. Now, the other part of this is we've said in the past that we can eliminate constant forces or constant forcing by measuring from static equilibrium. So we've said that when the forcing on an equation of motion is constant, it can be eliminated by measuring from static equilibrium. And for that, I'll refer you to this problem that we've shown below. Right? This was actually done in one of the previous lectures. We had a block and a disk. And we had gravity, right? So gravity was essentially pulling this block down in the equilibrium state. When we measured the response in terms of x, then what we found, and in x here, essentially if x is equal to 0, the spring is unstretched, we found this constant forcing term. If we measured from that, then that constant forcing term drops out of the equations of motion. So in this problem, constant forces, and in particular the constant gravitational load, constant forces lead to constant forcing in the equations of motion. Forcing on the equations. And again, I want to distinguish between the forces, which are like gravity, and the forcing, which is this term on the right-hand side of the equations of motion. So in this case, these can be eliminated by a proper change in coordinates. Right? So if I measure from static equilibrium, the resulting equations don't have a forcing term on the right-hand side. So that I'd like to contrast with the present problem. And here, constant forces. Well, these actually produce variable moments. If you look at the moment produced by either gravity or the external force, it depends on where the bar is. So if the bar is horizontal, for example, vertical, then gravity produces no moment. If the bar was vertical, then the external force would produce no moment. So because they produce variable moments, they cannot be eliminated. So really the question of whether or not a term can be removed or eliminated or neglected by a change in coordinates comes down to the equations, not the actual force itself. So in this case, this constant force produces a constant forcing. But in this case, these constant forces produce a non-constant term in the equations of motion, one that depends on the configuration itself. So, not all constant forces produce constant forcing. On the equations in the equations of motion. It's important to know when you can neglect a physical effect like gravity. So in this lower case, we can neglect gravity and measure from static equilibrium, or cases where we can't neglect gravity. And really, I think it comes down to, does that constant force also produce a constant moment, right? So if it does, here, there's actually no moment produced on the block, or if you had something like that acting on the disk, it would produce a constant moment. Constant forces that produce constant moments, we can neglect them by measuring from static equilibrium. But if the constant force produces a non-constant moment, as in this example, then we need to include gravity in the modeling. You know, for me, my silly question is, if I moved this system to outer space, right, where there was no gravity, would it behave the same as it does here where there is gravity? That's just kind of a way of checking yourself. So that's it. That's a lecture that we've looked at a bar, and we've linearized that motion, and we have developed equivalent linearized equations of motion based on the static equilibrium position. Right, so that's it for this lecture. Of course, if you have any questions or feedback, please let me know. I hope you've enjoyed it, and I will talk to you soon. Take care. Bye.